Talk about characterizations of the GTEC.
Okay. Thank you very much. So I'd like to start by thanking the organisers very much for the opportunity to speak here. So at the original Random Geometry conference, I was really at the beginning of my PhD, and I learned such a lot of stuff, and it was really what motivated me to try and do something in this area. So it's really nice to be giving a talk here. So what I'm going to talk about today is a characterization of the planar Gaussian free field, and this is joint work with Nathaniel and with Gurab Ray, who's in the University of Victoria. Okay, so this next slide is the point where I would try and convince the audience that the Gaussian free field is an interesting thing to work with. But I guess here I don't really have to do this. I'm sure everyone already believes that the Gaussian free field is a kind of fundamental and beautiful object. But for the purposes of this talk, it's kind of important to remember, just how ubiquitous the Gaussian free field is, in the sense that we see it popping up from all sorts of different places, so arising as a scaling limit from lots of different discrete models which are on the surface seem potentially unrelated. So we've already seen this morning the connection between the Gaussian free field and SLE curves and conformal loop ensembles. There's a connection between the Gaussian free field and random matrix theory through the characteristic polynomials of the matrices. We see it arising as a scaling limit of random height functions, so the height function in the Dimer model, or the interface in the Ginzburg-Landau model. And finally, as we saw this morning and last week, and as I'm sure we'll continue to see throughout the week, there's a very deep connection between the Gaussian free field and the theory of quantum 2D quantum gravity, random surfaces, and the scaling limits of random planar maps. Okay. So, in light of this, is a kind of natural question to ask is there something that explains this ubiquity? Why do we really see it popping up all over the place? And what I'll try and convince you in this talk is that, in fact, the Gaussian free field is the only possible object which satisfies some very natural properties you'd expect from the scaling limit of discrete models. Okay, so I'm sure no one really needs to see this, but I'll just use it to fix some notation. So I'm always going to be working with a Gaussian free field in some arbitrary simply connected domain with zero boundary conditions. So how would we like to imagine this? We maybe want to think about it as a Gaussian field on the simply connected domain D, which is a random Gaussian function which is centered and has a given covariance structure. And we want this to be given by the Dirichlet-Green's function. So this function GD, at the point x, y, it's just the expected amount of time that a Brownian motion starting at x spends at the point y before it leaves the domain. So this is the Green's function with Dirichlet boundary conditions. But as we all know, in fact, because the Green's function is blowing up logarithmically on the diagonal, there's no way that we can define a random function, a random Gaussian function with this mean and covariance structure. So if we want to make rigorous sense of the Gaussian free field, we have to let it live in a bigger space of objects. So the way we can rigorously define the Gaussian free field is as a Gaussian generalized function, or a Schwartz distribution. So we don't know how to evaluate it at points, but we know how to test it against smooth functions, and with a specific mean and covariance structure. So it's going to be centered, and we're going to be able to say what's the covariance if we test our field against any two test functions, and it's going to be given by integrating against the Green's function. So alternatively, and this will be kind of important for the rest of the talk, we can think of the Gaussian free field as being some Gaussian process indexed by the set of test functions in the domain. Okay. And one comment which is going to be important later again is that the Green's function itself actually is characterized by some properties. So it's true that if you fix one of the variables in the Green's function, so say I fix the second variable to be equal to y, then as a function in the first variable it's actually a harmonic function in the domain minus the point y. And in fact this property, together with the fact that it blows up logarithmically on the diagonal, are actually enough to characterize the Green's function. Okay, and if we assume that it has zero boundary conditions. Okay, I'm not going to make this more precise because I'm not going to use it precisely, but this is just something to bear in mind. The Green's function itself has a nice characterization. Okay. Right, so what are the key properties that I claim characterize the Gaussian free field? So the first one is conformal invariance. So what does this say? Well, if I have some domain D and another domain D prime and a conformal map between them, if I take a Gaussian free field on the first domain, I can also look at the field that I get by taking the image of this original field under phi. And then I can ask the question, how does this field phi of h relate to a Gaussian free field in the image domain? And conformal invariance just says that these two things have exactly the same law. And this is a kind of natural thing to expect from a scaling limit of discrete models, because it's kind of in general, this is something that is believed that should be exhibited in the scaling limit for a kind of very wide class of models. Okay, and the second property, which is also natural in the framework of thinking about the Gaussian free field as a scaling limit, because a kind of discrete version of this property is satisfied by many discrete models, is this domain Markov property. So we already heard a bit about it earlier. What does it say? It says that if we have a domain D and a Gaussian free field in D, and we also have some subdomain, which I've called U and it's in pink, then actually we have a decomposition of the Gaussian free field into a sum of two independent parts, one of which has the law of a Gaussian free field with zero boundary conditions inside this domain U, and one of which is a harmonic function in U. Okay, and these two things are independent. And for the setup of the rest of the talk, I want to state this domain Markov property not just in terms of a decomposition of the field inside U, but actually inside the whole domain. You can still do this. Now you think this HU is going to be zero everywhere else outside U, and it's just a Gaussian free field with zero boundary conditions inside U. And the field phi, well, outside of U, it's just going to be exactly equal to the original Gaussian free field, and inside, when you restrict to the inside, it's going to be a harmonic function. Okay, so that's the domain Markov property. And what's the result? The main result is that these two properties in fact characterize the Gaussian free field. Okay, so as you can imagine, I've got loads of different domains lying around and generalized functions, and to actually state this precisely requires a little bit more work, but this is kind of the takeaway message that I want to get through. Okay, but now let me actually say it properly. So what's the setup? So we assume that we're given a family of laws, one for every simply connected domain of the complex plane. And for each such domain D, we're given the law of HD, which is going to be a linear stochastic process indexed by test functions. Okay? So we know how to test it against any smooth, compactly supported function in the domain. And for the sake of brevity, when I talk about this law, I'm going to say it's the law of a field. So I'm going to describe a linear stochastic process indexed by test functions as just a field. Okay? And we make this following assumption about these family of laws. So the first two are exactly what I just described, these important properties of conformal invariance and the domain Markov property. So these actually just have exactly the same form that I stated in the previous slide. Conformal invariance says if I have a conformal map from a domain D to a domain D prime, if I take some field with the given law in D and look at the image of it under the conformal map, then the law of the resulting field has the same law as the given law in D prime. And the same for the domain Markov property. It just says if I have some domain D and some simply connected domain U contained in D, then I can write the given field in D as a sum of two independent things, one of which has the given law inside U and is zero outside of U, and one of which, when you think of it as being restricted to U, it's a linear stochastic process indexed by test functions that actually corresponds to integrating against some harmonic function. So that's the kind of precise statement of the domain Markov property that I'm going to use. And then we need a couple of other assumptions. So let me just skip the third one for now. I wish I could skip it forever, but I can't. So the last one is the Dirichlet boundary condition. And so we really need this. This is to kind of rule out fields like, for example, a Gaussian free field with 3 boundary conditions or something like that. So we want to assume that our field has 0 boundary conditions. But actually we're just assuming we have this linear stochastic process. It doesn't have boundary values. So we have to think of some sensible way to say what it should mean to have 0 boundary conditions. And the way that we do this is kind of hopefully seems reasonably sensible. We assume that our process is centered, and also that if we have some sequence of test functions which are behaving nicely, not blowing up, and whose support is converging to the boundary in some symmetric way, then we assume the variance of our given field tested against such a sequence of functions converges to 0. And hopefully you believe that's sensible. If we did have some nice smooth function with 0 boundary values, this should be the case. Okay, and the final assumption is this assumption number 3. It's kind of a regularity assumption. So we make the assumption that for any domain D and any test function, actually the value of our field tested against that function has a finite 4th moment. Okay. And the reason we need this is for a technical reason. Somewhere in the proof we need to use a Kolmogorov continuity type argument to extract the continuity of some process. And for this we make use of this 4th moment assumption. But I want to emphasize that in fact we really believe that this is a kind of a purely technical condition, and you should be able to get this kind of regularity because of the conditions we've already assumed on the field. But for now we have to have this moment assumption in there. And the final thing, so it's clear, we have some bilinear form which takes any 2 test functions f and g to the covariance of our given field tested against f and g, and I'll denote that bilinear form by kd. Okay, and we finally make the assumption that this bilinear form is a continuous bilinear form on the space of test functions. And again, if you're thinking that your linear stochastic process is actually some kind of generalized function, this is a sensible assumption to make. It's not so strong. Okay, and so the result is, which is with Nathaniel and Gurab, is that if you have these 4 properties for your family of laws, then actually they have to correspond to the family of laws associated with some multiple of a Gaussian free field. Okay, so that's the result. And just a couple of remarks. Okay, so the role of the assumptions I already discussed. Basically, we need all of them except the 4th moment one, which we shouldn't need so much. And yeah, I also just want to comment that we actually have an analogous result when we're in 1 dimension. So I mean we're looking at something which instead of being indexed by simply connected domains is indexed by intervals of the real line. And we have a similar thing which characterizes the Brownian bridge here. We assume that if we have a family of laws on functions on any interval of the real line, which satisfies a natural domain Markov property, the same one that the Brownian bridge satisfies. So if you look at the Brownian bridge restricted to some subinterval, the conditional law is just a Brownian bridge from 0 to 0 on that subinterval plus the linear extension of the boundary values, together with some translation invariance and the correct scaling. So under those assumptions, we prove that such a process has to be a Brownian bridge. So this is like a kind of 1-dimensional version of our theorem. And I should just say that actually in this case, we really don't need any regularity assumptions on the field. Well, we need something very weak, nothing like a 4th moment, and that's kind of contributing to our belief that we shouldn't need it in the 2-dimensional case. Okay, so because I'm going to lift up the slides and go to the blackboard, I'm just going to show this last slide now. So if you don't want to watch me talk about the proof and you want to think about these instead, you can do that. So there are kind of several natural questions you can ask going on from this. So the first thing, okay, I've already gone on about it a lot, the moments. Secondly, we've seen that we got something for d equals 1 and d equals 2, so it's kind of natural to ask, what about in more dimensions? What about if you change the boundary conditions? And another question which is maybe natural is that, in the probabilistic construction of 2D quantum gravity of David Kupiainen, Rode and Vargas, they also define a field here, which isn't the Gaussian free field. It's something different because they have a non-zero interaction term in the Liouville action, but they get a field which satisfies some conformal covariance properties, and perhaps there's some kind of characterization of this field as well in a kind of similar vein. And yeah, the final question is there some kind of stable version of the free field? And if there is it interesting? So in the case of the Brownian bridge, there's also such a thing as a stable bridge, and it should be translation invariant and satisfy some scaling properties, and also some version of the domain Markov property. In fact, I'm not sure exactly what it should be, but some version of it. So in one dimension, you should have these other processes which you should be able to characterize in a similar way. So a question you can ask is, can you construct a kind of stable version of the free field in 2 dimensions? Can you characterize it? What would be the right domain Markov property? And is it actually an interesting object to study? I don't know the answer to any of those questions. Okay, so now I'm going to go to the blackboard. I'm going to... Oh, magic. Okay. So is the statement of the theorem clear before I... Okay. Right, so I want to spend the rest of the time just giving some ideas behind the proof. Does this go? Yeah. Okay, so in fact the proof can be broken up into kind of 2 stages, which essentially in the end are completely independent. So I'll try and give a few ideas behind both of these. So there's 2 main steps. So the first one, you remember this bilinear form, which I called KD. This is just the covariance between my given field on D tested against F and tested against G. The first step is to show that actually this covariance kernel has the form of an integral kernel. So this is the same as integrating F and G against some function, which I'll call KD tilde of xy. Okay? And of course, what we would like to show in the end is that this thing is some positive multiple of the Green's function. Okay? So that's the first step, kind of identifying the covariance. And the second step is to show that this field is actually a Gaussian field, in the sense that as a linear stochastic process, indexed by test functions, it's a Gaussian process. So to show that H, this process is Gaussian. Okay, and clearly once you have these 2 steps, you have a Gaussian process and you've identified its mean and covariance, so you know exactly what the field is and you've completed the proof. Okay, so I'll try and give a couple of ideas behind both of these steps, although I won't have time to give complete proof, but hopefully you'll get some idea. So what about step 1? So if we just think about it for a second, if we had some field which was a nice smooth function, what would this KD tilde xy be? Well, of course, it would just be the expectation, because everything's centered, expectations and covariances are the same. It would just be the expectation of the field at the point x multiplied by the field at the point y. Okay? But what we have, it's not a nice smooth function, it's just this linear stochastic process. So the first step is to kind of think of a sensible way how you could get this KD tilde thing. Okay. So in general, if you have some generalized function and you want to approximate its value at a point, whatever that might mean, there are kind of various sensible things you can do. So kind of the most obvious is, you can integrate your field against any test function. So if you want to approximate the field at some point, you just integrate your field against some nice smooth function, which is like the identity in some small neighborhood of the point and is 0 everywhere else. And that's a kind of reasonable thing to do. So we could try and do something similar here, but it maybe will get a bit messy, and in fact, because of the assumptions we've made on our field, there's a very neat and natural way to approximate the field at a point. And it's the following. So if I have a point x in my domain, and I have some small epsilon, which is positive, this is kind of like the level of approximation I want to do, then I know by the domain Markov property that I can decompose the field in the ball of radius epsilon around the point x. Right, so I can write this domain Markov property, I can write the field in D as a sum of two things, one of which has the given law inside the epsilon ball around x, and one of which is a harmonic function in the epsilon ball around x. Okay? So now if I think about integrating, if I think about taking the average of the given field, whatever that, okay, it doesn't really make sense, but if I think about what it would mean to take the average of the given field on some circle of radius just a little bit smaller than epsilon around x, then you can think what the contributions from the two parts in this decomposition would be, right? So the first guy, it has the law of the given field in the epsilon ball around x, but remember we assumed that the given field had zero boundary conditions. So if I take its average on some circle which is just a tiny, tiny bit smaller than epsilon, this basically shouldn't have any contribution. Okay? And this part, well, this is a harmonic function inside the ball of radius epsilon, so of course if I take its average on a circle, it's just going to be the value at the centre. So this leads you kind of naturally to the following definition. So I'll define h epsilon delta of x just to be equal to the value of this harmonic function in the decomposition evaluated at the point x. And for the reasons that I just described, we can think of this, and probably this is always how I'm going to refer to it, as the circle average at radius epsilon around x. And of course, once we know that it is a Gaussian free field, this is going to be exactly the circle average. Okay? But at the moment we've just defined it through the domain Markov property, and I claim that this is kind of, as epsilon gets very small, it's some sensible approximation to the field at a point. And in fact, to show step one, it's enough to prove the following. So this is going to be our aim. We want to prove that the limit as epsilon tends to 0 of the covariance of these circle averages at two distinct points is actually equal to some positive multiple of the Green's function. Okay? Right, so for the sake of time, in fact, I'm going to leave it just at a proof of this aim, and from here you can deduce fairly straightforwardly, it turns out to just be some kind of straightforward analysis, the full statement of step 2. Okay? So I hope you believe me that this isn't too hard. At least, hopefully you believe that this is a kind of sensible thing to try and prove. In fact, proving this aim in the end, because of the continuity assumption we made on this bilinear form KD, is actually enough to give you the full statement of step 1. Okay, so yeah, I'll just explain how you can prove the aim. And I'm lying, in fact, I'm probably going to skip something in the proof of the aim as well. But I'll try and explain something. Okay. So the first thing to do is, I've got this limit which I want to be equal to the Green's function. Well, the first kind of sensible thing to do is show that the limit actually exists. Okay? And in fact, the reason why this limit exists comes out quite easily from the domain Markov property. Okay? So firstly, I'll claim that the limit exists. Okay, for all, if I take some distinct x and y, this limit is going to exist. So why is this the case? Well, if I take x and y, and I take epsilon, which is kind of small compared to the distance between the points x and y. Maybe epsilon is something like this. Okay. Then what is the this thing that I want to show the limit of exists? By definition, remember these circle averages were just defined through the domain Markov property. This is the expectation of the harmonic part in the domain Markov property in the epsilon ball around x, evaluated at x, multiplied by the same thing if I did it in the epsilon ball around y. Okay, so this is the thing which I want to show has a limit. And the point is the following. So because epsilon is small compared to the distance between the 2 points, I can draw some like bigger balls around them with radius, I'll call it epsilon 0, and epsilon 0 is going to depend on y. It's just going to be like the distance between x and y divided by 2. Okay, and the reason that I've done this is because if we want to work out what these harmonic functions in the domain Markov decomposition in the epsilon balls are, an alternative way of doing this is I can first apply the domain Markov decomposition in the epsilon 0 balls, and then take the field part in that domain Markov decomposition and apply the domain Markov decomposition to that in the epsilon balls. And the point is that everything that happened in this second step in these two separate balls is completely independent. And so it doesn't contribute anything to this expectation here. And so in fact this expectation can be rewritten as an expectation which depends only on epsilon 0 and not on epsilon at all. Okay? And of course, you know, this means you have something constant, so it has a limit as epsilon tends to 0. Okay, so more precisely, you know, I can write the field, I can do a domain Markov decomposition in the epsilon 0 ball around x. I can write it as a sum of two things, a field part plus a harmonic part. Okay, and then I can further do the domain Markov decomposition for this field inside the epsilon ball to write it again as some field part plus some harmonic part. So I've called it h tilde plus phi tilde. Right. And the point is that actually once you've done this, you know that this harmonic thing here has to be equal to this phi b epsilon 0, so the harmonic part in the first step, plus this extra thing phi tilde. And why is this the case? Well, it's basically because if you assume that you have a domain Markov decomposition, then it has to be unique, right? I've given you two different ways to write the field inside the epsilon ball as something with 0 boundary conditions and a harmonic function. So of course this has to be unique, right? Because if you had two different ways of doing it, the difference between the harmonic functions would be harmonic with 0 boundary conditions. Okay? So the key idea is you can iterate the domain Markov decomposition to write this harmonic function phi as a sum of two harmonic functions. And I could have done the same thing around the point y. So I could have written this as phi b epsilon 0 y plus phi tilde tilde, okay, coming from first decomposing inside the epsilon 0 ball around y and then iterating. But the point is, in this first step, the two field parts in these two domain Markov decompositions are of course independent. Okay. And so that means that this field phi tilde and the field phi tilde, this harmonic function phi tilde and this harmonic function phi tilde tilde are also independent. And everything has mean 0, so this expectation is actually just equal to the expectation as if I'd done it in the epsilon 0 ball. And of course now the nice thing is this doesn't depend on epsilon at all. Okay, so just to recap, what we've done is we've taken two distinct points x and y, and we've looked at the thing we want to take a limit of, and we've shown that actually for small enough epsilon, it's constant. Okay, so obviously this limit exists. Okay, So you've got that this limit exists, and you want to show that actually it has to be a multiple of the Green's function, and you can guess from what came up earlier how you're going to do this, and this is basically to use the characterization of the Green's function, that if you fix one of the variables then it's harmonic in the domain without the value that you fixed, and plus some property that it blows up logarithmically on the diagonal. Okay. So my second claim is that actually this limit, which I call kd tilde, if I do this, if I look at it as a function for fixed x, as a function in y, it's harmonic in the domain without the point x. Okay, and in fact, from this point, you can go on to prove that it has to be the Green's function in kind of several different ways, none of which are particularly difficult. So for the sake of time, I'm going to just show you this and leave this here. And if you like the idea that it's characterized by blowing up logarithmically on the diagonal plus harmonicity, you should get some idea in the next part of the talk why it blows up logarithmically. Okay, so I'm just going to show why it has to be harmonic. So why is this the case? Well, actually it's a very similar idea to what I just described, right? So in fact, to show that it's harmonic is enough to show that it satisfies the mean value property, right? So we want to prove that if I have a point x and I have a point y and I have some ball of radius r around y, okay, then actually the value of this function at the points x and y is the same thing as if I took the average over the boundary of this ball around y. Okay, so this is just the mean value property. Okay, and proving this is enough to show that your thing has to be harmonic when you fix x. Okay, and why is this the case? Well, by basically exactly the same reasoning that we just saw, this kd tilde of xy, I can draw some other balls here which separate like this. So maybe this is radius r2 and this is radius r1. Okay, I can write this kd tilde as the expectation of the harmonic part in the decomposition in the ball of radius r1 around x, evaluated at x, multiplied by the harmonic part in the domain Markov decomposition in the ball of radius r2 around y, evaluated at y. Okay? And similarly, I can write this thing at x and z as exactly the same thing, except I replace where I put y before with a z. Okay, so the reason why this is true is kind of subtly different to in the previous proof, but essentially the idea is exactly the same. It's just this idea of iterating the domain Markov decomposition. Okay, but now you see, if I rewrite this expression with the kd tildes replaced by these expectations, having this mean value property exactly just corresponds to having the mean value property for this harmonic function here. But of course it's a harmonic function, so it satisfies the mean value property, and you get the mean value property for your 2-point function. Okay, so yeah, I'm sorry that it's not like a complete proof, but hopefully it gives you some ideas. So this is how we go about doing step 1. And now I want to finish off by talking a little bit about step 2, because this is the cool one. And actually, in the end, this is the one that kind of caused the most technical difficulty showing this Gaussianity. Okay, so for the Gaussianity, again, I'm going to state our aim slightly differently and leave it to you to convince yourself that this is enough. So our aim is going to be to show that if I take any endpoints in my domain and then I look at the vector taken by the circle averages around all of them, then the aim is going to be to show that this vector is actually jointly Gaussian it's a Gaussian vector for all epsilon small enough, basically so that the epsilon balls are separated. Okay. And again, it's not too hard from such a statement to prove that actually your process is a Gaussian process. Okay, so why should this be the case? So to illustrate the idea, I'm just going to take the really simple case where the domain is the unit disk. I just have one point, and that point is 0. Okay. So I'm in the disk, I have 0, and what I'm interested in are the circle averages at kind of different circles around this point. So the idea is the following. It's just to define the process xt to be equal to the circle average at radius e to the minus t around the point 0. Okay? And if we know that it's Gaussian free field, we know this is going to be a very nice thing. Okay, so what can we say about this process? Well, firstly, at time 0, e to the 0 is 1, so we start off by taking the average around the boundary, and of course, because we've assumed 0 boundary conditions, this is 0. Okay, so we have that x0 is equal to 0, and we also know, because of our assumption, that x is a centered process. Okay, but now the nice thing comes, right? Because of the domain Markov property, if I look at the increments of this process, in fact, these guys are going to be independent, right? Because if I want to do take the circle average at time t plus s, I could first do it at time t, and then do it inside this circle. And this gives me, and just because I've assumed independence in the domain Markov property, this gives me actually that the increments of this are independent. Okay. And now I can also use the conformal invariance to say that the increments actually only depend on the ratio of the two circles that you're considering. Okay? So conformal invariance implies that the increments are stationary. So we're looking good because we have a process starting from 0 with stationary and independent increments. And remember, all we want to show is that at some time it's a Gaussian random variable. So at the moment, all we can say is that this thing is some kind of centered Levy process. But in fact, of course, what we want to do is show that it's a Brownian motion. And this is where we have to use our fourth moment assumption. Basically, because of the assumption of fourth moments, we can apply a Kolmogorov continuity criterion to show that there exists some modification of x which is continuous. Okay. And I want to point out that essentially this is the only place we use the fourth moment assumption. So in step 1 that I described before, we don't use it. Okay. But now everything is good. We have a process satisfying all these things. Of course, it has to be a Brownian motion, run at some speed. So in particular, if we look at the value of the process at any time, corresponding to the circle average at any radius, this is a Gaussian random variable, which was the kind of thing that we wanted to show. Okay, so that's nice, but of course we want to show something more complicated, and it turns out that in this kind of toy baby example, we got rid of kind of a lot of the problematic things. So there are kind of two ways in which problems come up. So what's the most obvious one is I just did it for one point, and we want to do it for a load of points. So more than one point. And the second thing is actually I really made my life a lot easier for myself by taking the point 0 in the unit disk. Okay, kind of surprising, this really made things easier because say I took some other point in the unit disk, right? I could try and repeat the same argument, so I can draw some circles around this point. But then I hit a problem, precisely when I hit the boundary of the domain, right? Because after that I can't draw circles that stay in the domain anymore. So I could, I could take this kind of biggest circle, and I could run the circle average process inwards from here, and I could deduce in exactly the same way that this has a continuous modification, it has stationary independent increments, it's a Brownian motion. But the problem now is I start from the circle average on this biggest circle, and it's not 0 anymore. So I have a Brownian motion, but it's not starting from 0, it's starting from some arbitrary random variable. And if that guy isn't Gaussian, then this tells me nothing about the Gaussianity of the process at later times. So it's not so useful. Okay, so they're kind of the problems, and first I'll explain how you might try and get around it in this case, and then maybe the idea for multiple points won't seem so wacky. So you've got this problem here with the circles, and how can you try and get around it? Well, what we really want is some process which starts by taking an average on the boundary of the domain. So actually what you can do is you can try and, after this point, oh, that's terrible, draw some things which are no longer circles, but they're kind of smoothly deforming contours which deform to the boundary of the domain. Right? And now instead of taking the circle average, I'm just going to take the harmonic average as viewed from this point x. And in fact, if I want to define this harmonic average using the domain Markov property, just like I defined the circle average, I do it in exactly the same way. I do the domain Markov decomposition inside the contour, and I evaluate the value of the harmonic function at the point x. Okay, so I can now define a process, where you take the harmonic average on these circles which start on the boundary and move inwards. And after some time, they actually correspond to circles around the point x. Okay. So for the same reason, I can show that this has a continuous modification via some kind of horrible technical estimates. It's going to be centered. It's now going to start from 0, which is what I wanted, but I've lost the domain Markov property and I've lost the stationary and independent increments. But in fact, now I can say something, okay, it's not quite as strong, but I can still say that this process is a martingale. And moreover, the quadratic variation of this martingale is deterministic. And why is that? Because how it's changing at any given time just depends on the shape of the domain at that time, okay? Which is a deterministic thing. So I have some continuous martingale with deterministic quadratic variation, and in fact this is enough, because if you have such a martingale, its value at any time is a Gaussian random variable. Why is that true? Because you can reparameterize time such that it's Brownian motion, and importantly, this time reparameterization will be deterministic. So in fact, doing this is enough to show that these circle averages, because after some time these are really going to be circle averages, it's enough to show that these things are Gaussian. Okay, and finally, just to very quickly conclude, what about if you have a load of points? So I want to look at kind of like the joint circle average. So if I have, say, like points here, 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 what I really want to do is I want to take averages over small circles around these points, okay? But I only know how to work with simply connected domains. So in fact, I'm going to kind of approximate these circles by some funny looking domain like this, and take some smooth sequence of contours which are deforming, from the boundary into something like this. And then as time goes on from this, these little sticks are getting skinnier and skinnier and skinnier. And showing that kind of, if I take a harmonic average, weight from each of the points added up and weighted in some way, then this is going to be a Gaussian random variable by kind of exactly the same arguments. And in the end, this is enough to show that the joint circle averages are jointly Gaussian. Okay, and I should say, actually, in order to apply the fourth moment estimates to get the continuity, we needed to define such a deformation that was kind of like nice enough, and actually it had to be quite nice because we need this strong estimate. And we couldn't actually, it's kind of obvious that you should be able to deform the boundary into this alien guy as nicely as you want, but in fact this ended up taking us quite a lot of thought, and one of the fun things we had to do in the project was actually construct such a deformation, which we ended up doing in a kind of probabilistic way. Okay, so since I'm out of time, I think I'll stop there. Thank you very much for listening.
So are there any questions?
Why do you really use conformal invariance? It's really at the end, because at the beginning it's much more like scale invariance on me, right?
Yeah. Yeah, so certainly in the first step we don't use it.
Yeah.
I mean, in the second step we really do use it to show that this martingale has deterministic quadratic variation.
It's really when you do this deformation.
Yeah. So in fact, also if we just needed to do it for one point at 0, we wouldn't need a conformal invariance. But we need something more. Yeah.
Why do you need a fourth moment in that argument? It kind of looks to me like you just need to show continuity of a one-dimensional process. You just need a moment bigger than 1.
So I mean, we definitely don't need a fourth moment. We kind of, just at some point we needed some moment, and it was easiest to work with the fourth moment. Once we had a moment assumption, we just.
It seems to me like, why do you need a fourth in that particular argument instead of something smaller?
I mean, I'm saying we could have a smaller moment, but I think you would need a moment greater than 2. And since it's greater than 2, I think we just didn't. Anything greater than 2 is too big.
It needs to be an integer and it needs to be even.
Huh?
It needs to be an integer.
It needs to be an integer, yeah.
And it needs to be even, because otherwise you're not measuring a size. You don't have something positive.
Okay.
4 it is.
But 4 is because you can compute things.
Exactly.
Yeah.
Technical assumption.
But actually, if we yeah, okay. So in this, we need if these properties, stationary independent increments plus fourth moment, allow us to conclude it's a Brownian motion. But equivalently, if we had Brownian scaling in there as well, then we could do without the fourth moment and show that it was a Brownian motion. But actually, showing that you have Brownian scaling seems to be a non-trivial thing.
And if you want to get rid of it, another strategy is to say that if you have jumped somewhere, then you destroy conformal invariance. Is that the strategy? If you have something that involves point processes or are living at points, then you can't be. Is that the?
Well, in the sense that the conformal invariance should somehow tell you that you have Brownian scaling, and then this means you can't have jumps. But to say there's a strategy would be overstating the state of it at the moment.
Let's thank Helen again.